Welcome to our fluid mechanics lecture under the topic Statical Stability of Floating Bodies. And in this video, we will have a short review of our lecture and we will answer the sample problems 1 to 3. Okay, so we have here a floating body in the upright position. So here. A floating body is acted upon by two equal opposing forces. These are the body's weight acting at the center of gravity. So this is the body's weight, W, acting on the body's center of gravity, and its buoyant force, BF, okay? And it is acting at the center of buoyancy. And that center of buoyancy, or B sub O here, is located at the center of gravity of the displaced liquid. So as you can see, our center of buoyancy here is located half of the draft, or the depth of water here. So this is D, or the draft, and the location of BO is half of the draft. When these forces are collinear, so here, the forces W and the forces BF, it is collinear, meaning they are in a straight line. They are collinear, the body floats in an upright position. Okay. However, when the body tilts due to wave or wind action, the center of buoyancy shifts to its new position. So this is the tilting position, and the center of buoyancy, B sub O, shifts to its new position, which is B sub O prime. So let's name it B sub O prime here for the new position of center of buoyancy. Okay. And the two forces, the W and buoyant force, which are no longer collinear, produces a couple equal to Wx. So the W here is no longer collinear with the buoyant force. Therefore, we can see that the weight is always acting on the center of gravity of the object. This is the G, this is W. Therefore, our force now produces a couple which is equal to the W times its distance from the line of action of the buoyant force. So this is the line of action, and the distance there is, let's say, x prime. So let's name that x prime, and that x prime is located from the center of gravity to the line of action, so x prime. And let's name this sidewise shifting, the distance that the new center of buoyancy traveled. Let's name that as x. Okay. Now the body will not overturn if this couple makes the body rotates towards its original position as shown. So if this W is located here, wherein it tends to rotate the body to its original position, therefore, okay, it will not overturn. But it will overturn if this W is located here. Okay? So it will overturn if the W is located here, wherein it will not turn in its original position. The point of intersection between the axis of the body, so this is the axis of the body. So this is the axis, the straight line here. And then when it tilts, this is still the axis of the body. Okay, so this is the body's axis. The point of intersection between the axis of the body and the line of action of the buoyant force is the metacenter. So where is that line of action of the buoyant force? This one here. So this is our line of action of our buoyant force. So this is the buoyant force here. And the intersection is what we call the metacenter M. So M, metacenter. The distance from the metacenter, this M, to the center of gravity of the body, G, is called the metacentric height. So mg is the metacentric height of the body. Mg here, the line mg is equal to the mb, so m to the base. So m to the base, and that is minus gbo. So gbo here. Should be MBO. Okay, MBO plus or minus GBO. So this is our GBO here. Okay, so that is our metacentric height. Now if okay, it says here that if M is above G, so if M is above G, so here we have M above G, or this one here, M is above G, what will happen? The body is stable. Okay, so if M is above G, the body is stable. But if M is below G, the body is said to be unstable. So if this M here goes in between G and BO here, so if M is here, located there, therefore the body becomes unstable. Now how about if the M coincides with G? If M coincides with G, it is said that the body is just stable. So just stable when M coincides with G. Okay. The stability of the body depends on the amount of the righting moment, which in turn is dependent on the metacentric height mg. When the body tilts, the center of buoyancy shifts to a new position, naming it as B sub O prime. The shifting also causes the wedge V. So these are the wedges. Okay, so these are the wedge. So those are our wedges. So the shifting also causes the wedge to shift to a new position. The moment to the shifting of the buoyant force, BF, Z, is mass equal to the moment due to wedge shift. So here is the theory of the wedge shift. So here it is. The moment of the shifted wedge is equal to the moment due to the buoyant force. Buoyant force BF times X. Remember that the X here is the displacement here, the X. Okay. The displacement from the original position of B sub O to the new position of the B sub O. So that's the X there. Whereas our BF prime, so what's our BF prime here? BF prime is the value of the buoyant force on one of the wedges. So there's two wedges here, but we will take only one buoyant force, which is the submerged one. Okay, so that is BF prime. And then 2/3 of B, or that is 2/3 of the base. So the 2/3 of base here, so given the B, so that's the location, that's the distance of the wedges. So the S here, okay, the distance of the two wedges is equal to 2/3 of B. So that's the theory of the wedge shift. Okay. Since the metacentric height mg is dependent with MBO, the stability of a floating body therefore depends on the moment of inertia of the waterline section. It can also be seen that the body is more stable in pitching than in rolling because the moment of inertia in pitching is greater than that in rolling. Okay? So, this is the MBO for the upright position, and we will solve for the moment of inertia. Now, the moment of inertia is taken from the waterline section. Okay? This is the MBO for the tilted position. So, as you can see, given the angle of tilt, theta. Now, as for the moment of inertia, what will we consider? So, as mentioned, it says there that the body is more stable in pitching than in rolling because the moment of inertia in pitching is greater than that in rolling. So, when we say pitching, here is the movement of our body. So, this is the pitching and this is the rolling. So, it is more stable. Why? Because the value of the I is greater in pitching. So, if we are going to take the moment of inertia of the pitching here, so if this is our motion, our neutral angle, neutral axis will be here, right? This becomes our neutral axis. Now, given this is our neutral axis, our I becomes, so if this is given as B, okay, if this B and then this is L, being the length of the body as L, given L, and this is the B. Therefore, the I for pitching, I for P, is equal to base, so that is B times the height or the L raised to 3 divided by 12. Whereas when we take the rolling motion here, so this is our rolling, right? And then this becomes our neutral axis. So this is now our neutral axis. So this. So if that is our neutral axis, our I for rolling, IR, is now equal to the, what becomes the base? It's the L. And then the B raised to 3 divided by 12. That's why the moment of inertia of the pitching is greater than that in the rolling. So it is more stable here than in the rolling. So what are we going to use? What are we going to solve now? Of course, we will solve the one with the less stability in order to find the greatest values, the maximum values. So in order to get the maximum value of forces, we will go to the ones with greater instability, which is this one. So we will solve for the moment of inertia using the I for the rolling. Okay, let's solve now the sample problems, numbers 1 to 3. So we have here, number 1, if the center of gravity of the ship in the upright position is 10 meters above the center of gravity of the portion underwater, the displacement being 1,000 metric tons and the ship is tipped 30 degrees, causing center of buoyancy to shift sidewise by 8 meters. Find the location of the metacenter from the bottom of the ship if its draft is 3 meters in the initial position. B. Find the metacentric height. And C. Find the buoyancy moment. Okay. So, what are the given here? We have the 10 meters. So the figure is not given, so you need to visualize. So in the upright position, the center of gravity is 10 meters above the center of the gravity of the portion underwater. So what's this? Center of gravity of the portion underwater. That's the B sub O. So CG is 10 meters from B sub O. Okay? And the displacement is 1,000 metric tons. What's this? that is the volume displaced. So that is VD, volume displaced. And 30 degrees here is actually the theta, causing the center of buoyancy to shift sidewise by, shifting sidewise by 8 meters. What's that? That is the X. That's the distance traveled from the B sub O up to the B sub O prime. Now find the location of the metacenter M from the bottom of the ship if the draft is 3 meters. Draft is 3 meters in the initial position. So we can have the figure. So let's have them here. So given the draft as 3 meters. So this is the draft of 3 meters. Oops. And then the center of buoyancy. Let's put the axis first here. Yeah. So this is our center of gravity. So around here, let's say this is our G, center of gravity. And for the center of buoyancy, B sub O here. So obviously this is 1.5 and 1.5, right? So this is for the center of buoyancy. So this is 1.5 and then this is 1.5, and for C, center of gravity to center of buoyancy, that is 10 meters. Okay. And it says there, find the location of the metacenter M from the bottom of the ship. So this is our metacenter M. So we're looking for the value of H here from the bottom of the ship. So H. And then, given the theta, the angle theta there, so when it is tilted, okay, there we go. This is our center of, or this is our metacenter M. This is our 30 degrees tilt. 30 degrees tilt. Okay. And then this is our center of buoyancy, center of gravity G, and this is 10 meters. Then we have our new center of buoyancy. Let's name it here. And then this sidewise shifting of 8 meters. Of course, this is right angle there. So 8 meters sidewise shifting. This is B sub O prime. Okay. So this is MBO M. So this is MBO. Here we can find the distance MBO by having this triangle. So by having this triangle here, we can find the value of MBO, given 8. So this is MBO, so sign. As you can see here, H is equal to the MBO, so this is MBO plus 1.5. So MBO plus 1.5. So from the triangle, we can find here the value of MBO as, so sine 30 degrees equals 8 over MBO. Therefore, value for MBO now is equal to 16 meters. Therefore, H is equal to 16 plus 1.5. So H is equal to 17.5 meters. That's the value of H. Now, let's find the metacentric height. So, what's the metacentric height again? Metacentric height is mg. So, here, mg. So, we can find here mg. So, this is A. For B, mg is equal to mbo minus, so MBO minus 10. So that is equal to 17.5 or 16. So be 16 MBO. So be 16 minus 10 is equal to 6 meters. So that is mg. And that is 6 meters. So 6 meters. For letter C, find the buoyancy moment. So what do we mean by buoyancy moment? What moment is that? Going back here. Buoyancy moment. So what's the difference between the among these three kinds of buoyancies, moments. So, say moments. For the buoyancy moment, the buoyant force rotates at G, or the center of gravity. For the moment of the wedge shift, it is the couple moment of BF prime, or that is the buoyant force at the wedge. And then for the moment of the center of buoyancy, let's name that as MBO. The buoyant force rotates at the center of buoyancy. So there's a difference between the two, the buoyancy moment and the moment of the center of buoyancy. For the buoyancy moment, buoyant force rotates at G. For the moment of the center of buoyancy, buoyant force rotates at center of buoyancy. Now for the problem, it says there, find the buoyancy moment. So what we're looking for here is the MBF rotates at, or that is the buoyant force rotates at center of gravity. So we will find the the buoyant force rotates at the center of gravity. Where's the buoyant force here? So this is our buoyant force. This is our buoyant force, and this is our x prime. The distance from the center of gravity to the line of action. Line of action here. And of course, this is perpendicular. Okay? Perpendicular. Therefore, our letter C, MBF, is equal to the buoyant force times the x prime. So we need to find the value for the x prime. So for the x prime here, that is, of course, there's 6 meters there. Therefore, we can find it now as sine 30 equals x prime over 6. Therefore, x prime is equal to 3 meters. Now, how about the buoyant force? Now, the buoyant force is equal to gamma volume displaced. So, what's our volume displaced? So, gamma water. Gamma water. The volume displaced is the 1,000 metric tons. So, how much is 1,000 metric tons in cubic meter? Well, buoyant force, volume displaced, 1,000 metric tons, that is 1,000 kilogram in 1 metric tons, and there's 1 cubic meter in every 1,000 kilograms. So, cancel kilogram, cancel metric ton, cancel 1,000 there. Therefore, volume displaced is 1,000 cubic meters. Therefore, we now have the buoyant force equals 9.81 times 1,000. Therefore, buoyant force now is equal to 9810 kilonewton. Finally, we have our MBF moment, M and then BF now is equal to buoyant force 9810 times the x prime of 3 meters. So MBF is equal to 29,430 kilonewton meters. So that's for number 1, example number 1. Let's go to example number 2. A rectangular barge 15 meters long, 8 meters wide, and 3.6 meters high has a draft in seawater of 2.5 meters. Its center of gravity is 2.70 meters above the bottom. Determine, letter A, the initial metacentric height. Letter B, if the maximum transverse angle of heel is that one end or the top corner is just submerged in water, find the sidewise shifting of the center of buoyancy. And letter C, final metacentric height. So there's a difference between the initial, okay, the metacentric height of the initial and the metacentric height of the final position. There's going to be a difference. Okay? And what's the given here? The dimension of the barge, 15 meters long, 8 meters wide, 3.6 meters high. We have given a draft. Okay, the draft here, seawater, 2.50 meters. And the center of gravity is 2.7 meters above the bottom. Again, there is no given figure, so we need to visualize it. So there you go. Here is our barge. So the what you're looking at here is the front. Okay. So this is what you can see at the bow. This is our bow. So this, or you can see it also at the stern. Okay. So that is the dimension. We have here the 8 meters wide and it is 3.6 meters high. The draft given is 2.5 meters in seawater, and the center of gravity is located 2.7 from the bottom. So from the bottom to the center of gravity, 2.7 meters. Then we're looking for the initial metacentric height. We're looking for mg. Okay. So how do we find the value of mg? So we have MBO minus GBO. So MBO minus the GBO. So again, we must recall here that for the B sub O, okay, so this is half of the draft, 2.5. So that is 1.25. So 1.25 here, 1.25 here. Therefore, our letter A is mg is equal to MBO minus the GBO. Now we can solve for the GBO now. For the GBO, that is equal to 2.7 minus 1.25. And that is equal to 1.45 meter. Now for the MBO, so for the MBO, we have the formula for MBO for the upright position as the moment of inertia all over the volume displaced. So this is one of the formulas, right? So this is one of our formulas. So again, what will we consider for the moment of inertia? It's at the pitching action, the rolling, I should say, the rolling action. So the rolling action here being, okay, so this is our barge in the waterline section. So where is the neutral axis? So this is our neutral axis. So NA, this is 15 meters by 8 meters. Okay. So that is equal to base times height raised to 3 divided by 12 all over VD. So MBO is equal to our base here is 15. So 15 times the height is 8 raised to 3 divided by 12. The volume displaced is okay, so 15 meters long, the 8 meters wide, and the draft is 2.5. So 2.5. So MBO is now equal to 2.13. So this is 2.13 meter. Okay. Therefore, we can have now our MG now as equal to 2.13 for the MBO minus the GBO. So this is now our MG. Our GBO is 1.45. Therefore, MG is equal to 0.68 meter. So that is the answer. for the initial metacentric height. Now, how about B? How do we understand B? If the maximum transverse angle of the hill is that one end, the top corner, is just submerged in water, find the sidewise shifting of the center of buoyancy. So what are we looking for here? Sidewise shifting of the center of buoyancy, that is the x. We're looking for the value of x. Here we go. So this is the tilted body. So this is for our letter B. Here is our line of action of the metacenter on the buoyant force. There we go. And then we have a sidewise shifting. So we have the sidewise shifting. So from here, the buoyant force, center of buoyancy here, up to the new center of buoyancy. This is x, and this is perpendicular. There we go. So we're going to look for the value of x. Now, what is the angle of, what's the tilt, angle of tilt here? Where can we find that? So as you can see, it says there, the one end or the top corner is just submerged in water. So this is the top corner, which is just submerged in the water. And from this, we can find the value of theta. Okay. So how do we get the value of theta? So this is our original water line. Remember, so this is our water line here, and then we put it here. Okay. So that's our original water line. So the distance here, the submersion here, so what's the value of this? So we can find that the value there is this one. So what is 3.6 minus 2.5? That is 1.10. So this is also 1.10. This is 1.10. And since this is our base, 8 meters, we can divide it into 2. 4 meters and 4 meters. Now you can now find here the triangle. This triangle here. And let's use that triangle in solving for the angle. Okay, so let's go to letter B. So for the triangle 1.1 for, this is the angle. There we go. So tangent theta equals 1.1 divided by 4. So theta is equal to 15.38 degrees. So that is shift tangent of 1.1 divided by 4. So 15.38 degrees. So having been able to find the angle theta, we can now find the value for x because we can solve for MBO. So for MBO, in the tilted position, we have formula for that. And what's the formula for the MBO on the tilted position? So we have there MBO is equal to b squared over 12d times 1 plus tangent squared theta all over 2. So that's our formula for MBO in the tilted position. So our B is 8 squared divided by 12 times our draft is 2.5. 1 plus tangent squared theta 15.38 all over 2. So MBO is now equal to, so that is 8 squared 12 times 2.5, 1 plus tangent 15.38 squared all over 2. 2.21 meters. So MBO is 2.21 meters. Therefore, from the triangle, so from this triangle now that we have the value for MBO and we're looking for X, we can use their sign. Okay. We can now use here sine 15.38 equals X over 2.21. Therefore, our X now here is, that is 2.21 sine 15.38, so 0.59 meter. That's for letter B. Can we use this formula in getting the value for MBO here in the upright position? Yes, we can use that. If we put the value for theta equal to 0 because it's in the upright position. So, or let's say this one here, or okay, MBO is equal to 80 squared 12 times the draft 0.5, 1 plus tangent squared 0 over 2. So what is MBO? So our MBO here is 80 squared over 12 times 2.5, 1 plus tangent 0 squared over 2. So the answer here is 2.13 meters. And this is the same with the answer here. So they are the same. So you can still use this formula even in the upright position. Just put here the value of theta as 0. Now for letter C, what's the question for letter C? It's looking for the final metacentric height. So the final mg. So the final mg here, what do we mean by the final mg? We're going to use the value for MBO final. So the value for MBO initial 2.13 here is different from the value of MBO final. So we can use that in letter C because mg for letter C is MBO minus GBO. So MBO 2.21 minus GBO does not change. So 1.45. So the GBO does not change, only the MBO. So 0.76 meter. 0.76 meter. That's for example number 2. Let's go to the example number 3. Okay, so we have here the center of gravity of the barge shown. Okay, so the figure is shown is on the midsection 2.70 meters above the bottom of the barge. So what do we mean by that? The center of the barge shown, center of gravity of the barge shown is on the midsection 2.70 meters above the bottom of the barge. So it means from the bottom of the barge up to the center of gravity, and that is 2.7. So we will put here 2.7 now. So let's just say 2.7. And given the dimension of the barge, which is 12 meters long, 4.5 meters wide, and 3 meters high, the draft is 2.4 meters. If an outside force heels the barge until point A, this point A here, is just at the water surface, compute the letter A, moment of the wedge shift, B, moment of the center of buoyancy shift, and C, value of overturning and righting moment. Okay. So the draft given here is 2.4 meters. So 2.4 meters, this is the draft. 2.4 meters. And the barge is 3 meters high. So there you go, 3 meters high. And 4.5 meters wide. So B is equal to 4.5 meters. Okay. So given the draft of 2.4, therefore the center of buoyancy, there you go, center of buoyancy is 1.2, and then 1.2. So we're looking for the moment of the wedge shift. Now for the moment of the wedge shift, just as we mentioned a while ago, that is MBF prime. Now for the moment of the center of buoyancy, that is the moment at the center of buoyancy, MBO. Okay. So for letter A, let's find the value for MBF prime. So MBF prime, that is equal to the buoyant force, that is the wedge, right? And then 2/3 of the base. Okay. So the situation here is that an outside force heels the barge until point A is just at the water surface. So something like this. So the A here, point A, is just at the water surface. And our wedge here is this. So these are our wedge. So BF prime. It's BF prime. Say, yeah, let's put it like that. There you go. So BF prime, BF prime. And the distance here is 2/3 of B. 2/3 of the base. And this is our center of gravity, and this is our center of buoyancy. Okay? So there. Let's look for the value for BF prime. So this is our BF prime. So what's the volume there? So BF prime. So BF prime here is actually the gamma water times the volume of 1 of 1 wedge. Of 1 wedge. So that is the gamma of water, 9.81 times the volume of one of the wedge. So 1/2, and the wedge here is 4.5 divided by 2. And then the length is 12 meters. And what's this? So this is 3 minus 2.4, that is 0.6. So this is 0.6 because we have here as 0.6 here. So that's 0.6. And then the 2/3 of the base. 2/3 of the base being base 4.5. So what's the value of MBF prime now? 9.81 times 1/4 times 4.5 times 12 times 0.6 times 2/3 times 4.5. So 238.38 kilonewton meter. So 238.38 kilonewton meter. So that's the value for MBF prime. That's for letter A. Letter B, moment of the center of buoyancy shift. So moment of the center of buoyancy shift, so that is B. So B is that is MBO. We're looking for MBO, and that is buoyant force times the X, the sidewise shifting. So we're going to look for the sidewise shifting first. Now where it is? Where is it? Let's solve for GBO first. GBO. Let's find the angle. Let's find the angle first. So we can find the angle from this triangle. That's the triangle. From this triangle. Our triangle is 0.6, and this is 4.5 divided by 2. That is 2.25, and then this is our angle theta. Therefore, tangent theta is equal to 0.6 divided by 2.25. Therefore, theta now is equal to shift tangent of 0.6 over 2.25, 14.93. So, theta is 14.93 degrees. So, we can solve for MBO. MBO is equal to the base squared, 4.5 squared, 12 times the draft being the 2.4, then 1 plus tangent squared 4.93 divided by 2. So MBO is equal to 4.5 squared, 12 times 2.4, and 1 plus tangent 14.93 squared times 2, so 0.728. 0.728. Now let's check where our meta center is located, because let's see. So GBO is this one here, GBO. So GBO is equal to the this is 2.7, so G to the base, so that is 2.7 minus the here, the 1.2. So GBO is equal to G to the base minus the 1.2 here, so that is equal to 1.5 meter. So GBO is greater than MBO. What does it mean? If GBO is greater than MBO, therefore our meta center is located here in between GBO. So this is our meta center. Meta center M. And this is our line of action for the meta center. Now, having this as our meta center, therefore our buoyant force is located in this line of action. So this is now our buoyant force. So if this is our buoyant force, the X that we're looking for is located here. So let's make it bigger. Let's expand that figure. So this is our line. Line of action. So that is our line of action there. And this is our axis. Okay, there we go. And this is our meta center. Meta center M. This is our center of gravity G. And then this is our center of buoyancy B sub O. And then, so as you can see, this is our sidewise shifting X, and this is our, let's name that as X prime. And then the angle here is the same, so angle here is 14.93. And then we have the value for MBO as 0. So this is this is 0.728. So from this, we can now find the value for X. So sine of 14.93 is equal to X over 0.728. So X is now equal to 0.19 meter. And then we have the buoyant force. So take note, our target here is BF times X. So BF now is equal to gamma of water times the volume, so 9.81. Then the volume being 2.4 for the draft times the base 4.5 and the length being 12. So buoyant force is equal to 1271.38 kilonewton. Therefore, MBO is now equal to 1271.38 times the X of 0.19 is equal to 241.56 kilonewton meter. So that's for letter B. Now how about letter C? The value of the overturning and righting moment. So where can we find the overturning and righting moment? So from our discussion, it's located at the center of gravity. So since we're talking about the center of gravity, so the force that we're going to use there is the buoyant force, but our x there will be the x prime. So we're going to find the value for x prime. So what is x prime? So sine of 14.93 is equal to x prime. What is mg here? So mg or gm. So our GBO, a while ago, we got that as 1.5, right? So our GBO is 1.5 meters, a meter. Therefore, this is for this triangle. So for this triangle, so we have 1.5 minus 0.728. So x prime is equal to, so that is 1.5 minus 0.728, and that is sine 14.93. So that is say 0.2. Say 0.2. So we will use x prime as 0.2 meter. Okay? So letter C. For letter C, M is equal to BF x prime. So buoyant force 1271.38 times x prime 0.2. So M, the overturning and righting moment, that is 254.28 kilonewton meter. So that's example 3. Okay, so tune in for the part 2, which is we will solve the examples number 4 and 5. So that's it for this